Hello everyone. Today I'm going to present a paper about how to use machine learning to help to predict the success of the leads for a company. This is the agenda for my presentation. In our days, technology is growing at a fantastic rate, so it's almost mandatory for the companies to adapt themselves to new approaches to keep themselves competitive in the market. In every company business processes, much data is getting created every day, and this is a handy tool to innovate and improve the performance of a company. So we must get and analyze data. So using machine learning techniques is a great way to learn more about our business and to improve our decision assertiveness. The core of this work is to identify the better possible way to predict the success of leads and the best ideal proposals conditions for the future contests. Here it is a good definition about what is machine learning according to Andrew Burkhoff. So, the main tools used for data preparation were cross-validation, data correlation, SMOT, ADASI, and TOMEC. And the best machine learning used models were support vector machines, random forest, C5.0, neural networks, and AdaBoost. The CRISP-DM, that stands for Cross-Industry Standard Process for Data Mining, is a standard process for data mining and modeling application projects. This model's purpose is to perform extensive data mining projects with fewer costs, more reliable, more repeatable, and more manageable, and to improve speed execution of the project processes. CRISP-DM has 6 phases: business understanding, data preparation, modeling, evaluation, and finally, deployment. The purpose of this project was to help a company to improve in lead selling performance. The company stored their information in scanned and PDF files where they keep the results of the past contests. I dedicated some time to understand the company business routines and some standard motivation aspects that usually win contests. The data used on this project was on the following documents: preliminary reports, final minutes, and that on final reports. From those documents, we retained the numerical and descriptive information of the context that gave us some of the data and some of the variables. We also used public platforms to collect data about the clients and the competitors, and we retained financial and descriptive information about the rival companies and the clients. For instance, we retain sales volume of technology from the rival companies, and the amount spent in technology from the clients was recorded in the dataset. To store all the information, we created a web application supported on ASP.NET Model View Controller with direct access on the database. The company in question sells their own software called GNU, that is a low-code platform that generates code to quickly build a web application. The project was programmed with R with a lot of R packages. Now, speaking about data preparation tools, there's a list of the most relevant ones on this project. The cross-validation method allows to select k-subsets uniformly sized from the data. One of the k-subsets is left out in every iteration because the cross-validation is going to build a model using the chosen subset to evaluate the model on the remaining k-subsets. In the end, we'll get k-performance measures that we obtain by testing a model on data that we used for model development. Then, analyze the correlation between normalized variables is a great way to avoid autocorrelation. That means that some of the variables explain the same, and this causes redundant models. One of the barriers in this project was the lack of observations. It was hard to get the 101 observations from the available documents in the company. So, we used artificial data augmentation techniques to increase the data samples to train the algorithms. SMOT is an oversampling approach that generates X the training data. Besides increasing the data volume, the minority class is oversampled. AdaSim is based on SMOTE. This algorithm was designed to reduce the amount of unbalanced data between classes and adjust the classification limits. And finally, TOMEC is an algorithm of undersampling. The main objective of this algorithm is to eliminate edge instances that have more probability to getting incorrectly classified. It can be considered a data cleaning tool. Here we can see the graphical output of cross-validation techniques. We used several data partitions to perform cross-validation, and the ideal partition number that offered better results was 10 partitions. We tried to perform some training and testing with only 5 variables, but the results were poor. So we decided to introduce 5 more, that is the next recommended number of variables, and we have found the top 10 best variables to use in our dataset. So these are the top 10 found variables. Here is a quick graphical illustration that shows that there is no autocorrelation between the top 10 variables. So that's a good indicator to keep going. The real data was 101 observations that we split in 70% for training and 30% for testing. We applied SMOTE and TOMEC over the 70% dedicated to training, and we applied AdaSim and TOMEC to the exact same dataset. And as we can see, it generated a lot of more samples in SMOTE TOMEC case and just a few observations on AdaSim TOMEC. Here is a visual example of what SMOTE looks like. The blue dots are the original dataset, and the black circles are the new dataset with more observations that respect the relevant information of the original dataset. Using R software, the 5 models were trained, tuned, and tested with 3 different scenarios: the original dataset, SMOTE dataset cleaned with TOMEC, and AdaSim data cleaned with TOMEC. And the evaluation metrics used were accuracy, F1 value, balanced accuracy, area under the curve, classification error, and precision and recall. This table is the one that says it all. It's curious to analyze that in the other project concerning only the original dataset, the usually best one is the random forest. According to our results, the random forest was the best one if we didn't use artificial data. In our case, the best model that has shown the better accuracy, better F1 value, better balanced accuracy, and better balanced between precision and recall was the support vector machine with SMOTE TOMEC data. These two graphs follow the same ideology. The bigger the area behind the curves, the better the results and the precision. We can see that on precision recall graph, SVM dominates the rest of the models, and in rock curves, SVM and random forest are almost tied. So, the choice was evident, and we chose the support vector machine with SMOTOMEC training data. After choosing the best model, it was saved on the file to be used with new data, so we created an R script that runs commands on SQL. I will present the fundamentals of this script in the next slide. It was necessary to install and configure R services on SQL Server that will allow to run R scripts directly on the SQL Query Console. What the script does is, it selects and keeps the new data from the database, normalize the data with the same values that the model was trained, upload the model from the folder in the server to the SQL R console. It predicts the winning probability of the new cases using the SVM model, and finally it updates the table and the view to every user can view the predictions. Finally, this is the layout of the final solution. We can add new possible offers to specific contests, and when we press the predict button, it will call the script and predict the winning probability according to those conditions. We can say that we achieved the main objective. We found the best model, SVM with SMOTE, and stored at the company's server. Machine learning appeared to be a very effective way to improve leads prediction. And due to the lack of observations, artificial data augmentation techniques were used like SMOTE, AdaSim, and Tomek, and it allowed a boost performance. In related works, researchers used similar machine learning models, and the performance results were similar to the ones that we obtained in this project. The new element on this project is the performance boost due to the usage of artificial data augmentation techniques. And finally, for future works, here are some useful recommendations. It will be interesting to perform some unsupervised learning techniques with classification algorithms. We recommend performing some dimensionality reduction techniques such as principal components analysis or factor analysis. It will be useful to apply clustering methods such as k-means or dbScan. And despite not being mentioned on this paper, we performed the PCA, FA, and dbScan on the data just for curiosity, and it had shown promising results for improving data interpretation and visualization. I hope that this presentation was worth it. Thank you for your time.